Okay, so we were discussing about lab 1. Now, in lab 1, what the concepts that we learned in the last class should be used so that you can do this lab using Python. Um, Even if the online virtual lab is not available to you, you can do this on your machines because you can create these nodes on the same processor using two different processors. So that's fine. So here, what you need to do is in step 1, you have to define the two nodes. The master node will accept slave connection. It will check who is connected and also monitor the heartbeats of the slaves. If the slave is not responsive, it will mark that this node is dead and it's not responsive. Then it can also have a functionality of broadcasting membership changes if needed. The slave is node which will connect which will create will connect to the master. It will send the heartbeats regularly, and also it will send CPU and memory usage. And if the connection breaks between the slave and master, it has to request for a rejoin. Step 2 is for SSL, and we have discussed this in details why we need SSL, why it is important, and why we need trusted communication and encrypted messages. So and how do we do it? We also have discussed that you have a Python's SSL module which can be used as a wrapper for your sockets. You create the certificate and key files and use them for both master and slave. Then the third step will be how to set up the master. So here to create the server socket, then the master should accept the incoming connections, and once it has received the connection from the slave, it will store it in a table and then ensure that it keeps listening from the slave. You also can run a monitor thread which will periodically check if the slave is active or not. And if it is inactive for 10 plus seconds, you can mark it dead. So in slave, you have to create the client socket, the one we discussed in the last class, connect to the master. Then once it joins the node, the cluster, you have to start the heartbeat. In heartbeat, what you will do every 5 seconds, you will send the CPU usage and memory usage. So what should be the communication between the two? The slave should send master that join request that I'm slave 1, and it should send the heartbeat. That this is the heartbeat, and in a heartbeat it has to send CPU and memory information. You can have some messages from master to the slave, which are optional. That if the slave is offline or if it is dead or if that current cluster members are these. So master can keep printing those. And the last step is you have to check if slave is trying to connect. You have to send that okay, it has connected. You take it that its node ID and then you add it to the cluster and you ensure that the heartbeat of the slave is continuously monitored. So this is how the lab 1 is designed. You can try it using Python. Yes.
Ma'am, morning. Sorry.
Yes.
So these are all scenario. I think which are referring that we can do it on our local system. Is it something we
Yes.
need to deploy the multiple VM and then put them into cluster and then all day doing it, or how is it?
No, that we will do once the virtual lab is available. We can try this.
Hmm. But
In that,
in that case, how will we be creating the nodes and cluster and all this?
two sockets
In
using Python code we can create. One master, one slave.
okay, all
Yeah.
right.
On Yeah, this is just for your understanding of how the communication happens. You can try it out on your local system. And once the virtual lab is available, I will check and ensure that it is available to you by next week. We can try doing it in multi-node, kind of a system. This is only for your understanding of how sockets, how you can use the SSL, and how you can check the heartbeat between this slave and master. So how master keeps track of heartbeats. So just for the sake of understanding. And since we will move now to distributed computing in this next module, there we will use the this distributed systems which are available in your virtual lab. There are more, I think, 3 nodes. Okay, so yeah, so now to start with the distributed computing scenario, uh, we will learn what is MPI and we'll try using OpenMPI. We'll do some hands-on kind of experiments now, and which will give you an idea of how MPI works. Are there any people who have worked with MPI before? You can just raise your hands. So, okay. So I guess everyone are learning MPI today. Oh, so now MPI, as the name states, it's message passing interface. So the communication between different processes or nodes happens through message passing. And MPI, anyone remembers what MPI can be used for? We have discussed it this in the first class, I think.
Synchronization.
Message passing
Can you,
interface.
yes, where it is used? In what kind of
It's at some
computing?
process
Cross
communication
processing.
inside the system, and there is an open MPI that's on network, I think.
Okay, good. And what kind of system it is?
It's a
Yeah,
basic.
Yeah,
distributed.
it is for distributed computing.
Yes.
MPI we are learning for distributed computing. So OpenMPI, you can, as we said, you can communicate between different systems which are looked through network. So MPI is, uh, as you all know, the course is Introduction to Parallel and Distributed Computing. And through MPI, we will learn the distributed computing. Whereas with for learning the parallel computing, we have OpenMP, can which works for single system using multiple threads. We also have CUDA, which is meant for especially GPU computation, where you can run different applications on GPU, which are meant to use different cores, perform the same task using different threads. But MPI is for distributed compute. So the so this library uh, is used for different parallel computers, clusters, and heterogeneous networks. It it has tools available for you which can be used for communicating over network, which have different functions. We'll see some of these functions will execute the code also and observe how it works. So to start, the base of MPI or even OpenMP is a process. So we've discussed this. process is the instance of a program, and each process in this MPI will run a single program, and this is written in C or Fortran. The what is similar in process? Yeah, someone is saying something. Okay, so as you can see, there are different systems in this figure, and each of them is communicating through the network. So, and how the communication is done in message passing is you communicate using messaging. So you need special send and receive routines, which will send a message from one processor to another, or from the master node to the sleeves, and the receive will have to receive the message on the other end. So we'll see what kind of functions are available in MPI. So now, when you have different processors or different systems, you need to know who is the one who is sharing the message or sending the message. So identifying each system is very important, very critical to ensure that the system works. And to do that, we have a concept of rank. Rank is an identifying number. So all the decisions are based on the rank. That is, which process works on which data, you will know using the rank. So minimum MPI code will look like this. So here, as you can see, the first function is MPI init. This is very important. Whenever you start an MPI program, this is a very critical step where you have an init function which initializes the MPI environment. And if you have noticed, along with stdio.h, we have included the header file mpi.h. And then there is MPI code, whatever code you write, create a number of processes, send, receive messages, whatever. And then you have a function MPI finalize. This finalizes the MPI environment. And then you return 0. So this is the simple minimal MPI program where you initialize the environment and finalize the MPI. Do you think this is multi-threaded? Or multiple processes will execute this? We'll just try running it. Okay, yeah. So, how do you compile and execute MPI programs? You use MPI-CC. MPI-CC is a wrapper over the C compiler, which is meant for MPI codes. So, you give the program name, whatever program name that you have, .c file, and -o, and create a executable file. What happens if you do not give -o and executable?
It will create a.out.
Yes, it will create the default a.out file, and this a.out file you will have to give to MPI execute. Here you mention MPI execute, provide the arguments that you need. Now here, in this case, you are saying -np2. NP is number of processes. So here you are mentioning -np2, which will create 2 processes. And the dot executable will be the executable file that you are providing to your MPI. So now let's run this. Yeah, any doubts?
Ma'am, this
Is this
compiler
network? Yeah,
MPICC is by default with by default comes on the Linux, or we need to do something else
you will
for
have to
that?
install. You will have to install on MPI.
Okay.
Do we have any document containing all the steps required as far as MPS setup is concerned, which version to be used and so forth?
Um, I'll upload that on the sorry Tuxfila I meant. Yeah.
Right, and do upload Windows as well as Linux, both variants.
Okay.
Thanks.
Yeah. So the hello file. So what we have done, if you do not have, if you have only init, and a simple printf statement, is this video visible?
Yes. Yes.
Okay. So what we do, this is a MPI TC better hello -o. This is just a hello. So if we now run MPI run np
It's a hyphen NPM.
yeah. So it printed twice, right? But we do not know which thread is printed, how many, and which hello, right? Sorry. So here, to know which is the process which is trying to execute or writing this message, we need the rank. And to get the rank, we use MPI com rank. This MPI com world is a by default group. You can create more groups and you create the rank. And the size is the one which provides the number of elements or number of processes which are part of this group. So if we run this code, we'll have to first compile it. So is this visible output?
Yes, ma'am. Yes, ma'am.
Ma'am, MP
So
com
if you
word.
see,
What is this group for actually? Can you just little bit give an idea?
huh?
This MP
No,
com word.
group of four is the four threads are there part of this group.
No, no. This
Size of
in the code you mentioned MPI underscore com underscore word. Can you just give a little bit idea on that? What is this group for?
world. Okay.
Yes, yes. Word,
So
yeah.
so you can group your different processes in a group. So you can create a group and then add, have two, separate different processes and to have different groups of processes. You can create more than one group of threads or group of processes.
So this
So this is
MP
the
com word
default
is
one.
just an variable name you used, or it is
Yes,
somewhere you're calling something? Okay, it's a variable.
yes, it's a variable name, but this is the default one. You can create more
Understood.
different ones.
Ma'am, when we specify hyphen NP as 4, as
Hmm.
in 2 or 4, it
Yeah.
creates 4 instances, as in 4 processes, which are going to execute
Yes,
exact same code, is what you mean.
yes,
Those are
yes.
not threads, right? Those are not 4 threads. Those are
In this
4
case,
different processes.
since so four different processes, but since I'm executing on my system, which is a yeah single system, I'm calling it threads. But four processes basically you're creating.
Okay.
So four processes of single thread for this system, I would say.
4 processes of single thread.
One thread each.
1 thread each. 4 different processes, I mean. Yep.
Yeah,
Okay.
yes, yes.
Yeah.
Yeah.
Can you talk about what MPI init and MPI finalize do in a nutshell, as in what kind of
Yeah.
initialization is required, and at the time of finalization, what cleanup activity is done in a way? Can you just elaborate on that a bit?
Yes. So MPI init is a function which takes the arguments, if there are any arguments, required, such as the number of processes, and
Hmm.
it initializes the MPI environment so that you are able to use the MPI functions that are available to you. Okay. So including the whatever communication channels you need, whatever process management is required, that is set up with MPI init. Then MPI finalize, it's supposed to clean up the MPI environment. It will release all the resources that are used, and it will terminate if there is any MPI operation that is going on, it will terminate. So basically, it is like a shutdown to MPI runtime environment, which will ensure that all the MPI related activities which were initialized in this work are properly terminated. Okay. So
Okay.
hence the first function will always be the MPI init before any other MPI function, and final will be the MPI finalize.
Yeah.
Ma'am, will we see any kind of communication? Here, I believe we have seen how to create the processes. Now, how they
Yeah,
communicate is it
yeah.
coming? Okay,
We
okay.
will start. There are slides. Yeah, yeah. We'll see.
Madam,
We'll
as far
run a
as
few more experiments. Yeah.
right, as far as memory allocation is concerned, is there any role of MPI as far as allocation, deallocation is concerned?
So whatever memory is needed for, you know, uh, for the processes like the process names, for the process states and everything that will be needed for the MPI as well, right?
Mm-hmm.
So, and each of these processes uh, can access their private memory space, as well as what if there is any data exchange that will happening between these processes through message passing, that also memory will be utilized.
Okay, so in effect, MPI works as kind of a container which hosts number of processes in between, and there is kind of a channel between them via which the
Yes,
variable
yes,
values can be accessed
yes,
in a
yes,
way.
which are buffered. Yeah, there are buffers which store these values, and those can be exchanged.
Okay, thanks.
Yeah.
Ma'am, one more questions.
Hmm.
There are two questions. One question like, is there any way to tell, go and create this process on particular core, or is there any limitation to pass the numbers of thread to the program? It's based on the numbers of CPU or
Yes, number of CPU ports that you have, it will allow you. Now let's just try. Let's do this experiment, please. So now I said 8. If I say 32, yeah, created 32. With open entry, it will not allow, but API. This is a 16 code system, so it's allowing creation of, maybe it creates and closes. Okay, I'll yes. So I'll get, yeah, I'll clarify this of why it's
Okay. Yeah.
allowing. Okay, now, yeah, let us move to the communication.
Second part of the questions. Is there any way? Suppose I have 32 cores on my systems. Can we say go and run this particular process on core number 2 or core number 3, something like that?
Through MPI directly.
Yes.
At least, okay. At least I'm not aware of if that's allowed, because this is handled at compile time. The compiler then assigns
Cores.
yes, course. It may not even depends. Sorry, not even compile time. I think it will happen when you finally execute, because depending on what is the resource, because that's will be the task of OS, right?
Okay.
It will decide
Okay.
which resources are available and how to assign them. So that will not happen. That cannot be done through the code. At least I am
Okay.
not aware of such functions.
Yeah. Got it. Got it.
So yeah. So we have seen the minimum API program. Now, if you want to run the MPI program and find out the environment, about the environment, we can find it out by checking a MPI com size, which will give us the number of processes, and MPI com rank, which tells us the rank of the process, a number between 0 and 2, the size minus 1, that is the number of processes that use, which is with, we identify the calling process. So we've seen this code. So now let us start with the message passing. So in MPI, the very important part is how do you pass the messages, and you have different functions which are available to you for passing these messages. The first one, the first task is one process will send a message. Now the send function has these different parameters where you use pointer. The first one is the buffer. As I mentioned, the communication in MPI happens through buffers. So this buffer is the pointer to the data buffer that you want to send. So you will create a variable, and this variable pointer you will give in this MPI send message. This variable will have the data that you want to send. Then count is the number of elements you want to send. Then you have MPI data type. So you have to mention the data type of your element. Then the destination process rank, which process will receive this data. Also, you have to provide a tag. Tag is very important. Tag, if the tag does not match, then the process will not receive the data. So tag is very important in finding the matching receiver for the data that you send. Then you have to send the communicator, the group with which you are communicating. In this case, it will be MPI com world. So is this clear? Any doubts here?
Ma'am, can you come on earlier slide?
Yeah.
Yeah, so particularly the tag part, what that tag value, sender will decide a certain tag value, let's say 10, and receiver
Hmm.
knows that I want to look at tag value equal to 10. That way,
Hmm.
sender sends it with
Yes.
a particular marker. So tag kind of becomes a marker from sender and
Yes.
receiver perspective, and those values must match. Then only that receiver will process the message is what you're trying to come at.
Yes. Yes.
Okay,
Mm,
but the broadcasting part of it, as in let's say if there are four different processes running same piece, and if I do a MPI send, that would be from one process.
Hmm.
All the three processes are going to get the message per se, but either of them, based on the tag value, one of them is going to pick up it and process it, right?
Yes. Which wherever there is a tag match, only then they will receive it.
Okay, but
They
message will
can
be
process.
sent out to all the three in a way. It is
It
sent on
will be
network.
open.
Okay,
Yeah. It is open, and then
broadcast
receiver
kind of
will
a thing.
receive it. Yeah. There is a
Broadcast kind
special
of a thing.
function for broadcast also.
Okay, okay,
This is for one to one. Yeah.
Ma'am, I'm not
okay.
understanding this MPI common word communicator. Is there a
Yeah. So as I
designated thread which will
so,
communicate?
so yeah, as I mentioned, you can create the groups for your MPI where group of
Okay.
processes can be part of one communicator, which is like uh, this group of processes is something which whichever are part of this group can do the communication with each other.
Okay.
Okay,
Within the group
so
limitation is there, right?
yes, yes.
Okay.
So this MPI com world is something which is a group uh, global communicator, which includes all the processes that are in the MPI job. Okay, you also have an option of MPI com self, which is a communicator which includes only the calling process. You also can create custom communicators, which are user created groups, which will communicate for only specific operations. You can create those special communicators as well.
Mhm.
Okay. So how it helps is with this, it becomes easier to manage complex, parallel columns because if you are doing some operations in the context of group, those can be given to a separate group. Okay. Also, it helps you to scale your, computing because you can just add processes to a group and communicate only within the group. So, yeah. So that's how there are again other functions which where you can split the existing communicator and then you can create different functions for this communicator. So that these things are available, and so by default you can use MPI com world, which is like a global communicator. But if you want better performance and scalability, it is always advised to create a custom communicator for your specific case because global will communicate with all the existing processes. Sorry. Yeah. So now this is how MPI send works. Before we see the example, here MPI send is called a blocking function. Okay. Any guesses why it's called a blocking function?
It must be waiting until the message is consumed at receiver side, so it gets blocked till the time somebody reads it.
Yes. So that's the confusion I want to clarify prior to we moving the to see the example. It is not till the receiver receives it. It is only till it gets buffered. Okay. You
Okay,
send
okay,
the message, check if it is buffered. Once it gets buffered, okay, then it says complete. Process B may not even receive it. It's fine. But as long as it's
okay.
buffered, you are blocked till it is buffered. Especially, what if you have large amount of data to be shared? That time, the MPI is sent. If it is not able to buffer the data, then it will have to wait till someone receives it.
Okay. Okay.
But if
Got
it
you.
is a small message, it can
Mhm.
just get it buffered and then start communication with other message, or do some other competition task. So for receiving a message,
Okay, ma'am, I have one question. Can you remain on the earlier
yeah,
slide?
yes.
We have two processes in this particular example. There is something called as MPI A and MPI B. What are they exactly?
So for communicating between these processes, process A, process B, the buffering will happen with MPIs in the with the process of the library, right? From you know,
Mm-hmm.
which is which is separate from the process execution. The buffering where it happens with the system, that is what is shown here in MPI.
Okay. Does that mean for each process created, MPI creates another kind of a helper thread or helper process or something of that sort which takes care of buffering and reading the buffer kind of a thing?
Uh, we can
Ma'am,
yes.
I think
So
MPI creates a
huh,
transport kind of layer, right? Beneath the processes, something like it.
Mm-hmm.
That's what it creates, right?
Okay, but
yeah.
does that
So
get
the
created for each process is the question which I'm trying to come at.
yes, it will get created for each process. Each process will have its buffering system. So
Okay, okay.
yeah,
So it's kind of an external boundary for each process, as in via that boundary, the exchange happens between the processes effectively,
yes,
right?
yes.
Okay, and can
So
one more question
data
on
is
blocking? Mhm.
yeah,
Sorry, gone. Sorry, gone.
yes. Yeah, continue.
As far as blocking behavior is concerned, you said till the time message is buffered, it is going to block. But when forget about the message size, assuming the message size is smaller and buffer is good enough to hold that message.
Yeah,
Assuming that situation,
yeah.
if process A waits until the message is buffered and somebody reads it, if it does both, then won't it be even blocking in nature?
Can you repeat
So read, I
that
think, will
point?
happen once MPI A transfer it to MPI B, right? When it crosses the boundary,
So
and then process B will pick it up, right, ma'am?
yes, so this is MPI A and MPI B is basically the MPI library and not the
Mm-hmm,
process, right? So
mm-hmm,
this
mm-hmm.
library will buffer it, whatever the data is sent, it will get buffered. Until it is buffered, the process A cannot continue and do something else. It has to wait.
Correct.
Okay. As soon as the buffering is done, process A can then start doing some other task. Now, if some other process is ready to receive that time, it can receive the data. That's not a problem. But after the buffering,
Okay, and if the other process, the process B, receiver process in this case, if it doesn't read the buffer at all, and what happens
no,
as in
but
till
it will
Mhm.
because if you see the function here,
Okay,
MPI receive,
MPRSA will
you have
answer
to
that.
provide the
Okay.
buffer. Yeah,
Mhm.
you have a buffer. So
Okay.
the buff will have the buffer, the same buffer. You have to provide the count, the data type. The source will have the rank of the
Sending
process which is sent to
processes.
communicate, the
Mhm.
tag, and the communicator. And also you with receive you get a status. Status will tell you if the message is received or not, if there is an error. So status function is meant for that. So so the received data could be some variable where you provide the data. The number of elements could be you have to mention the different data types. The rank, if it is zeroth, the tag will have the must match value. the communicator and status. So we will see a status example later. First, we'll see an MPI read and send and receive example. So here, sorry. So you create the necessary, you know, the COM world you've created, the rank, the MPI request and status. We create a variable data, and now the process 0. So rank 0, usually we make the rank 0 as the master rank which is trying to communicate. So rank, if the rank is 0, you do the send. Sorry, this is I think I sorry, this is I send. I send is different. So yeah. So yes, in this you use you need only rank and the data. Here you are sending the process. The process 0 is sending the data. MPI sent as data variable with the pointer. The we are sending only one value, that is 100. So 1 MPI int is the data type. It's a integer value that we are trying to share. Then this is 1, the tag and the COM word. So now the next thread, if its rank is 1, it will receive the data. Here you provide the buffer for receiving the data, int receive data, the count, the init, int, sorry, then the tag and the communicator and also status. We'll run this code. So as you can see, the process 0 will send the data to 100 to process 1 and process 1 will receive the data.
So is this something we are creating two process in the same program and trying to communicate?
Yes, yes. And not the same program, same machine currently, same system.
Okay.
Ma'am, one question here.
Yeah.
MPI int. So for each data type which is supported, is there a MPI variant of it?
Yes, yes. I'll show that in the slide.
Okay, it would
What
come in.
options
Okay,
are there?
fine. And
Yeah.
then follow-up
Check.
question would be, okay, follow-up question would be, can we have user-defined types? As in, until that is there, we won't be able to send complex structures and all. But I think
Yes,
it will
yes.
be a follow-up
Yeah.
question. Yeah.
Yes, yes. You can create your user-defined types as well. So yeah, here as you can see, these are the data
Mhm.
types which are there. Character, short, int, long, and
Right,
whichever which are very common in most of the programming languages.
right,
So,
right.
but you can also create custom data types using MPI type create. Here, as you can see,
Hmm. Hmm. I see. I see.
right,
Yep.
or MPI type contiges, which help you to create these complex structures of arrays, or and then you can pack them as MPI pack.
Right. So in effect, for each type, we have a parallel MPI variant. So while messages passed across various processes, MPI long, as in using that type,
Yeah.
each process identifies what type of data is there and how I should read it in a way.
Yes.
Yeah. Ma'am, if we consider this byte requirement for, let's say, integer, typically it is 4 bytes on based on what type of machine it is. If we have MPI int corresponding to it, does it have more information than what integer holds?
MPI, if you use
See,
MPI,
right. Theoretically, MPI int is a wrapper over signed int, right?
yeah, yeah, yeah.
So is it
So
just an alias or it holds more information
it's
than
the
what?
same. It's the same. It's the same.
Okay, size wise,
It
as
is
in the
alias.
memory
Yeah.
requirement would be
Size,
exactly
yes,
same.
exactly same. Because it is, as I mentioned, MPI int is a wrapper over C compiler.
Okay.
So yeah, these
Okay.
things will be same as C.
Right. Was there any specific reason to create a wrapper? Can't we use the underlying types directly?
I think that the compiler designers will be able to answer for the MPI why exactly they, yeah, chose to create them.
Okay.
But yeah,
Ma'am, one more question.
maybe
Can you
they
go to
wanted to avoid any confusion with
can
the
you go back
other
the
C
program
code and this. Yeah,
Maybe. Yep.
program that just you execute in the
yeah,
code
yeah, sure. Yes,
VS
definitely.
Code?
Yes, I'll open that.
Here we are
Yeah.
doing we are creating two process in the same program. What
Yeah.
changes we need to make it if we have two files and like this is one file and same replica of this is another files, and we are trying to communicate two processes of two different programs. What
Yes,
changes?
we will come to that.
Hmm.
Most probably in the because we will be discussing distributed computing for next 2 3 classes. We'll talk about it in detail there. But
Okay.
this in this class we are just focusing on understanding how basic MPI programs work. What is the communication that you can do amongst processes using the MPI that you have. Okay.
Okay.
So
Okay.
we will then move to distributed computing system in terms of system level communication between the nodes that we will discuss in the
No,
later
I'm
class.
not. I'm not talking about the system level. I am talking about the two programs running on the same systems. They are creating two different processes.
Okay.
Like this is
So
the one MPI send receive and MPI send
yeah.
receive one something two program,
Hmm.
and we'll run both two program on the two different console, and we'll try to exchange the message between these two programs through the processes.
Okay. So
It's a
uh,
kind of distributed
this is
programming, but
this
on the
is
same machine.
so this is currently the same thing is happening here as well, right? These two are two different processes which are on the same system and are communicating through
No,
send and
but
receive.
this two processes created by the same program, like your one C file. But if I'm creating two different program and trying to communicate from one program to other program process.
In that case, you have to ensure that the com world, the group is same and the rank and this is consistent.
Yeah, that's I think that's answer. We need to
Yeah,
create two different group of the communications, and
yeah.
okay,
If you want two different, then two different, or if you want the same thing to happen, then they have to be in the same group.
okay, okay. I will give a try on that.
Yeah,
Yeah.
you try it
Ma'am,
out
as
and
far as,
share the experience.
yeah, as far as
Good morning,
current,
ma'am.
Yes.
Ma'am, so regarding
Uh,
for lab practice, do we have to install VS Code in our laptop?
no, for the lab practice, you can do it on the virtual lab that is available, and you may not need VS Code because
Okay,
there you will get access to Linux. Yeah,
sure.
this is
Thank
for yeah. I'm using a Windows system. That's why.
ma'am, one question here. As far as current program which you have shown is concerned, it
Mhm.
differentiates processes based on rank. Do you have a sample of program where we differentiate using the group as well as rank both, and then decide what needs to be done, kind of a thing?
Yeah, that's a good suggestion. I do not have that currently in my system, but will that is not real. It will not be that difficult. You can try it out, or I'll also have create one and share it
Yep.
or discuss it in the next class. But in today's agenda for the class, I do not have.
Okay. No
But
problem.
that's a
Yep.
nice suggestion that I can add for future classes as well,
Yep.
just to
Yep.
show that how the communicator is different. Helps you to divide two groups of processes.
Correct. Correct. That would bring out the master slave analogy in theory,
Yes.
right? And then there could be a number of slave nodes part of the other group, the slave group. And there could be
But
only one
no, no,
master.
no, 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 no.
Hmm.
But the communication does not happen between two different communicators. So
I didn't clearly follow
communication
that.
happens in yeah, communication happens only in one communicating group.
Oh, okay. Okay, I see. I see. I get you.
Yeah, yeah,
I get you.
yeah.
So that
If you want to
MPI.
divide the
Hmm.
if you want to divide the work between two different sets of processes, then you can use a communicator.
I get you now. Yes. That helps. Thanks.
Yeah. So okay, so now we have seen blocking blocking messages. Now we can see how unblocked messaging can work. So for that, you have which is known as yes. So okay, we will first discuss status. Yeah. So uh, how now this is an example uh, where we have process which is sharing the data, and here uh, here we are checking the status of after receiving the data. So how do you check the status? You have to first create the MPI underscore status variable. That this variable should be shared to your receive. Once you send this status to your receive or get the status from your receive, then you can check what the status that you have obtained. So for that you have to create two more variables. One is int source, which will give you the status.mpi source, and int tag, which is status.mpi tag. So which will tell you received messages from process ID, which is the source, and the tag. So we'll just run an example and see how it works. You can see it's the same code. So process 0 is sending data to process 1, and then we are checking the status of what is received by using source tag. And also you can get the count. How you can get the count is you have a function MPI get count, which takes the status, the the number of the data type, and the count, with which you can get what is the received data, the source, the tag, and the count using the status. So as you can see, process 0 has sent data 1, 2, 3 to process 1, and process 1 has received data 1, 2, 3 from process 0 with tag 99, and the count is 1. You can verify the tag here was 99, even if some random tag is there, it will be the same tag that you receive the data that you get from the status.
Ma'am,
Okay.
one question
So
here.
before, yeah, yeah.
MPI receive, the way MPI send from sender side until the message is completely buffered onto corresponding MPI A.
Mhm.
I'll call it as process for now. So until
This
that
is
message,
MPI compiler basically in execution. Oh, yes.
okay, MPI counterpart for A, until that
Yeah. Yes.
takes over the buffer data, as in the data completely, sender remains blocked. Similarly, if we consider the receiver part of it, then MPI B will get the data in a way, right? And then from MPI
Mhm.
B, the process B is going to read that data. So until that
Mhm.
read data is completely read, even process B will be in a blocked state. Is that correct?
Yes. From the time it starts receiving.
Okay, so it cannot process the data until it has completely read the buffer content. Once it reads, then only it starts
Yes.
processing further. The way it looks like,
Yes.
as in it's kind of a method call. MPI receive can be considered as a method call. It gets data and then it starts processing further.
Yes.
Okay, yeah,
So we'll learn more about this send and receive. So MPI send and receive have two types of options. One is blocking and non-blocking. So blocking send is MPI send and MPI receive, whereas non-blocking is MPI send and MPI receive. These are non-blocking communication. So what happens is you initiate a send operation but does not wait for it to complete. Whereas in non-receive, you initiate a receive operation but does not wait for it to complete. You let it happen in the background and you move on and do the other task. Okay. What do you think could
yeah.
be issues with non-blocking and where blocking might be useful, where non-blocking might be useful? Anyone?
Uh,
What are
non-blocking
the
communi- uh, Non-blocking is something like it's if data is huge and process is due to something else also other than sending the data. I think we can send the data using the non-blocking send operations and move ahead to do the other process.
yes, yes, and non-blocking?
Blocking is mostly used when data size is small or sample size is small. We'll send and wait for the acknowledgement and then ahead and do the processes.
Yes, yes. So uh, when so you have to consider different scenarios like and requirements. Or whether performance is a key criteria. I do not want to lose any CPU cycles in just waiting for the data. Then how what is the size of the data? So you know you can use non-blocking, especially for performance critical code, where you can send some messages and it ensures that as long as there is no significant performance benefit, it is fine. But you have to you can prefer using blocking for if there is a simple small code and it becomes easier to communicate and so understanding what is the specification of your MPI implementation and how it should handle blocking and non-blocking and how critical is synchronization. Is there any data races that are possible? All those things are important in choosing what kind of a function you want to use for sending and receiving the data. So you have MPI wait and MPI wait all functions too. These are used to wait for completion of any non-blocking operation. So if there is any non-blocking operation, you can use MPI wait, which will wait till your specific operation completes. So uh, and you have wait all where which will wait for all the non-blocking operations if there are multiple happening to complete. So uh, there is also MPI B send function, which uses buffering to store messages sent with MPI send. So this will allow the operation to return immediately, even if the receiving process has not executed at all. And um, you also have MPI S send, which is synchronous communication. So here, the what you do is you send a message and ensure that the message is not buffered, and the sender will wait until the receiver has posted that okay, I have received it. Okay, so this guarantees that the send operation does not complete until there is a matching receive which has been posted by the receiver. Then you also have ready communication, which is MPI IS send and MPI IRS send. These are two different send of send. This function provides you ready mode communication, where ready send is similar to MPI I send, but the sender does not buffer the message. It ensures that the receiver has already posted a matching receive. Because the receiver is ready to receive, you can use MPI IS send, where there is no buffering involved. Then MPI IRS send is similar to MPI receive, but it indicates the system that the matching send is already posted. The send is already there and hence it can receive it. So as I mentioned, wait is for specific communication to complete, especially in MPI I send and MPI I receive, which are non-blocking communication. You need to check if it is done or not. You use MPI wait and provide the request send and the status, which then gives you, once it is done, you can print send from process 0 is complete for a send operation. For a receive, again, you have to provide the request receive and status. So then it will say that process 1 received data from process 0 and stop. So let me show an example of I send and I receive. Here we have done I send and I receive. I don't think you will be able to appreciate how it works, because it's not a very complex code. But here you have to use MPI wait. So started sending data from to process 1. The send data is complete. Then the received data. So you finish the send first, and then the data is received by the next process. But they can do some other work while this is happening in the background. So if you want performance, then you can go for a I send I receive, as long as the data is sent and received and there is a wait function, it will get done, and whatever data that you are using or receiving should not be tampered, or there should not be some race conditions, or there should not be any specific needs for synchronization. Yes.
Ma'am, how is it different with the blocking one? Because ultimately here it's also we're waiting, right, to complete that sending by process 0, and then the process 1 is starting the receiving it. And similarly in the earlier one, the MPA send and receive, it is also, I mean, statistically it is, I mean, it is same, right? So until that buffer complete, then the receiver will start receiving the data. How, what is the base difference in both of this?
Yeah, that's an interesting question. Um, so I understand if you use MPI weight, it might, uh, create some deadlocks also. Um,
Yeah. So
so
ultimately, when we are saying that, okay, for MP non-blocking, we should use where the performance is critical. But at end of the day, like we are still going with the weight also, right? So that will process one other, I mean, second process will wait until that process one is completed, right? Sending the data.
yes. So now, yeah. So waiting for this non-blocking operations can impact its performance. Uh, but sometimes you still have to um, use waiting if you want to ensure that there is correctness and data integrity. You need to wait, but yeah, and
Can we have any
yeah, and
any
I
real-time
understand your
use case?
question.
Yeah, can we have any real life use case for these both where we can correlate and understand that?
Yes, so one could be, you know, uh, where let's say you have um,
Okay, I think no issues,
so
ma'am.
usually like no, I'm just
Mhm.
thinking about weather forecasting problem.
Okay,
So
okay.
uh, let's say if you have a weather forecasting problem, which where we are trying to wait for data from different sources like
Mhm.
satellites, radars, and we're trying to then use it in our forecasting model. Uh, so there, let's say you are if you are not waiting for the to receive the data and it's not complete,
Mhm.
then there could be inaccurate forecast, right? Then the
Mhm.
since this will the value that is predicted is makes no sense. So if you wait, you will have a better improved accuracy for your model, which will then ensure that there is better decision making for whatever forecasting that is given. So,
And in case
uh,
we use the blocking code in that weather forecasting scenario as well, so will
huh.
there be any issue?
So if you use the blocking code, then uh, now, okay. So again, how you divide your memory utilization for receiving this data, storing this data, if the memory that is being utilized for two different, let's say, satellite and radar is separate and can
Mhm.
do the communication without any risk of data getting corrupted, then
Mhm.
we can do the we can do the or
So,
non-blocking
so
forecasting system.
ultimately,
But yes,
wherever we manage
okay,
the
let's say,
memory level, right?
huh,
Then I think we can use for the non-blocking. Okay.
yeah, let us consider, let's say if satellite is sending the data, then
Mm.
satellite can send the data using a non-blocking function. Okay, that
Mm.
is fine.
Mm.
Receiving, you use the non-blocking function, but you wait for it to complete on the other
Mm.
end. For satellite to send, it can be non-blocking, but the receiver has to use a non-blocking function, but it has to wait for it to complete. Does that make sense? Or
Yeah. Yeah. I
what I'm
got
saying
Understanding.
is,
got the point. Yeah.
on one end you
Mhm.
can use the waiting, the other end can continue non-blocking.
Ma'am, can I explain my understanding about this?
Yes, yes, yes. Please go ahead.
Can
Yeah.
you go on the slide wherein you had that program, or can you go to the program which you showed up?
I I sent.
Yeah, the last program which you showed up.
Yes.
Okay, so can you scroll up a bit? Okay, so let's hold here. So as far as difference between MPI send and I send is concerned, I'll explain my understanding. So
Yes.
MPI send is going to send the data as in it will go to buffer, and until that data is completely filled up in the buffer, MPI send
Hmm.
method will not return, as in none of the statement after MPI send is going to get executed, no
Yes.
matter whether they are going to work with the data or not. Nothing. So this guarantees that the data, as in we are taking a very simple example over here, it is just an integer data, but assume a situation we have a complex data which we are trying to send. We want
Hmm.
that data to be sent in its format as is.
Mhm.
Nothing should change as far as the data is concerned. Then MPI send is going to ensure that nobody can tamper that data until that data is actually buffered onto MPI A part. Then only
Hmm.
the process will continue further over here. So that way we lose onto the CPU cycles until the data is actually buffered onto MPI A line, as in that node
Mhm.
or process in a way. But
Hmm.
with iSend, we trigger that send part. So data starts getting sent across. Now let's assume a situation wherein we have 1 second time required in order to just buffer the data, assuming it is fairly complex. So
Yeah.
iSend is going to start trigger that particular portion and just start executing the next instructions which are present in the code. That way, since data is something which is accessible to this process, there is a chance that data might get modified even before it is sent completely.
Hmm. Hmm.
Here we
Hmm.
save on to CPU cycles, yes, but there is a risk of data getting modified even before it is buffered completely on the sender side itself. So
Yeah.
the point which I'm trying to make over here is between MPI iSend and MPI wait, the buffering process of that data is going to get completed, but we are given a chance to do something which is just done, or which is done in order to save on the CPU cycles, but we need to be very cognizant about the fact that we should not modify the data which is actually in process of getting sent out. So
Yes.
I
Yeah.
think it
Yep.
needs to be a
Yeah. Yeah.
programmer's intelligence, as
Call
in
programmers call. Yes. And
do I need to ensure
it,
that nobody modifies the data? If that is the situation, I should use MPI send so that it gets blocked until the data is actually sent out. If
hmm
I'm sure that data
yeah.
is not going to get modified, I have a task which is absolutely independent of the data and I want to save on CPU cycles, I can do the in between processing,
Mhm.
Agreed. Agreed. Yes.
that
Yes.
kind of
Very
a
well
thing.
put. Yeah. Yeah. Yeah.
Yeah, and same should happen on the receiver side, as in if you scroll down now,
Mm-hmm.
I receive is also I receive is also going to work on the same analogy, wherein it will start receiving the data, but it has not received the data completely. But CPU is relieved to do some independent task in between the line number 30 portion. It will do something
Yes. Yes.
in between, which is not working on the received data per se. It is doing something else altogether, independent activity.
Mm.
hmm
So we save on the CPU cycles that way. We don't wait until the data is received.
Yeah.
So important part is if we want to completely receive the data and work on it, that's the only thing the receiver has to do. Then it will have to wait. So it has to be
Wait.
blocking receive. Once it
Mm-hmm.
receives it, it will start processing. But if the data which is being received is higher in the size and there are CPU cycles which are going to get wasted and there is a task which is independent of the received data, then this
Yeah.
particular analogy is going to help so that CPU cycles are
Agree.
saved.
Yes. 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 Very
Yeah,
well put.
one question. Yeah, thank you, ma'am.
Hmm.
One question over there. Can you just remain on the same page as in the same code?
Okay.
Now, I'll just talk through in context of receiver side. The question is applicable to sender side also. Let's assume that reception of data requires 1 second. So
Mm-hmm.
on line number 28, we starts receiving the data. On line number 32, we check whether the data is received in its integrity or not. Okay.
Mm-hmm.
So assuming it requires 1 second of time to completely receive the data. Now, whatever
Mm-hmm.
happens in between line number 28 and 32, if that takes more than, let's say, 2 seconds.
Mm-hmm.
So data requires, let's say, 1 seconds for complete reception. We are going to check whether the data is actually received or not at line number 32. And whatever is in
Yeah.
between, that takes 2 seconds, for example.
Mm-hmm.
Then though I have received the data after 1 second, 1 second period will be there, as in we are going to do some else computing, right? And then once that
Mm-hmm.
computing is completed, then only we on line number 32, we are going to realize that whether the data is received or not. But the data is received maybe a second before itself. So isn't that a risk of kind of using the cycles in between?
Yes.
Was I clear in my
It,
question?
it is. Yeah. Yeah. It is. It is a risk. It is a risk of losing the performance.
Hmm.
But then again, it will be the programmer's call.
Okay, I get it.
He has to
I
just
get it.
judge
So,
how much.
hmm,
Yeah. How what the trade-off has to be decided by the programmer.
exactly. So basically blocking and non-blocking variants, while choosing both of those two variants, one need to be very sure about what is more important, as in
Yes.
whether I should start as soon as I receive the data,
Hmm.
or it is okay if data is received, I spare some time doing something independent and then check whether data is actually received or not, and then start working on the data in a way. So that cognizance has to be there, right?
Yes. Yes.
Yeah, thanks.
Okay. So we've seen the communication modes. We have seen how wait works. Uh, this these are the other functions where as send is as you know is synchronized. So the data has to be received, and once it is received, you will acknowledge, and then the process A can proceed. The B send is where you use buffering specifically, where the programmer defines a local buffer, and if there is no even there is not a matching receive available, the process is blocked until the message is copied into the buffer. So, so, so source can start modification as soon as it is sent. The I sent, as you can see in this figure, those if anyone has not understood, this figure might be able to give you better clarity. So here the function will return immediately once the I send starts. It's the returning starts. The buffering continues. The synchronization continues, but the completion may happen later. But as soon as I send starts, you can start doing some other task. Similarly, the ISS send, which is again a non-blocking version of synchronization send. Here, it also returns immediately, but the S send happens in the background, and MPI test or MPI wait will wait till to ensure that the function is complete in the background. So there is another option, which is when MPI IB send, which is again a non-blocking send, where it blocks for neither copying the message to the buffer nor sending the message. Once you test it positive or wait, you can then modify the source data that you want to test. But it Once it's sent, it can immediately start doing some other task. So yes, when to use what? We have had a very detailed discussion on this. But to summarize, when there is a deadlock, non-blocking communication can help. When there is a race condition, blocking communication is important. Otherwise, the data will get corrupted. When you have some computationally expensive task, a non-blocking communication helps because this can improve your performance. MPI send, MPI send are top in the priority list as MPI decide what is best. And send and ISend is when the sender needs to know when the message is received and whether to avoid any kind of local buffering. So, and you have many of these send and receive options because they are meant for the fine tuning of the performance of this systems. Okay, so with this, we move to the next part of what if we want to broadcast a message? What if we want to send this message to multiple processes at the same time? So here we can think of a master-slave kind of a system where the master is trying to send the same data to multiple slave nodes. So as you can see in this figure, the P1 has A, B, C, D, and it is doing a broadcast so that all the processes now after the broadcast will have the same data. So this could be an example of if you are trying to apply some different functions on the same data, you take the data, give it to different processes, and ask them to apply a different function for each process. It could be, let's say, if you're trying to apply some different types of uh, image filters. So image data you share with different processes, and each process is applying the filter it wants to apply. So here in the broadcast, the first one is the buffer. Buffer is the data that you want to broadcast. Then int count will be number of elements. Now this buffer on the root will be the one which contains the data to broadcast. On any other which is not root is where the data will be stored after the call. Count will have the number of elements. Data type is we have discussed. The root we have to mention because this is the rank of broadcaster within the rank of all the total size of the communicators, and com is the communicator. We'll see 2-3 functions and then we'll go to the code. The next one is gather. Now in gather, as you can see in this figure, you have P1, P2, P3, P4. Each one has one element. And when you use the gather function, the root node receives all the data from all the nodes. So this function has a send buffer, which is a pointer to each process's data to send, where the data will be sent by each process. Send count, the number of items each processor will send. Send type, the data type of these items. Receive buffer, which is valid on root to receive all the data. Receive count, which is number of items expected from each process. Receive type, the type of data. The root, who is going to collect all this data that is received, and the communicator. Next one is gather to all. Here, what we do, all the 4 processes have one element each, and now all the processes in that communicating world want to communicate the same data to all the other processes. So here we use gather to all or gather functions. So here again, send buffer, send count, data type, receive buffer, receive count, then the data type and the compound. MPI reduce is another function which you can use. Now here what is happening? The data that each of them had is collected and a function is applied. The function could be any function, as you can see here. It could be a MPI sum, it could be a MPI minimum, finding a minimum, it could be finding a maximum, it could be finding the product of all the elements. It could be ending all the elements, or it could be OR, XOR, and there are few more functions which you can use with this reduction function. So this function you have to mention here in MPI op operation. Rest of the things remain similar to the other four functions. You can also create some special function which is using MPI op create. Here you can create a user defined operator which can be used for this different data. So there is reduction to all as well. Reduction to all, as you suggest, whatever function you are trying to use will be used, and you will do addition or any kind of Boolean operation on all the data and send it to the all the processes. All the processes will have the result of this operation. So we will try these before we then move to synchronization. As you can see in this code, you have the value. We'll first see broadcast. The broadcast value, if the root, if it's a root process, you broadcast a value 100 and using the function broadcast. So broadcast value 1, MPI in, root, MPI com world. The process that each process will receive this data. For gather, the value you want, the locally that you want to create, you create that value. Then you create a array which will gather all the values, and then you call the MPI gather. Here, each process will have a different value because that we have calculated by giving this rank plus 1 to each process. Then it will do gathered values will be collected here, and we will print each process's gathered values here. Process 1 gathered value. So we can remove this, as it will repeat again and again. And then the reduction part. So here we are using MPI sum. So let us run this and then try other things. MPI CC. Let's use 4 processes. What is happening? Process 0 is broadcasting value 100 to all the processes. So Process 0 received the broadcasted value first. Then process 0 started gathering the values from each process, and it also had a reduction. 4 plus 3 plus 2 plus 1 is 10. Process 1 received the, now then the rest of the processes received the broadcasted value. Let's run this again so that check if, yeah. We can change this function to, let's say, do prod Is this clear?
Here one question I have, like the broadcast process was sent out 100 value, and again it is self-receiving 100 only, right?
No. See, for broadcast sent 100 values, but gathered is gathering the local value. So gather function is collecting local values. So broadcast had shared 100. If you change this to broadcast value, then the process 0 will calculate, will gathered value will be also be 100.
Okay. So this local value, I mean gathered value is from other processes, right?
Yes.
Okay.
So for other processes, we created local value as local value is equal to rank plus 1. That's why it was collecting, 1, 2, 3 earlier. If rank is 0, local value is 1. Rank is 1, local value is 2, and so on. Is that clear? Because we are calculating local value as rank plus 1. So what is the buffer that you are using to give each of these function? Similarly, if you give the function in reduce value, if you give the function broadcast value, even the reduce value will change. Because it's product, it will multiply all 4. Is that clear? Okay, so let us move to synchronization.
Ma'am, one point over here. Uh,
Yes.
for understanding purpose, these examples are good, but is there any kind of real life or better way to kind of explain these methods? As in a real life example. For example, we are reading from a text file. We have 4 different blocks of integers, for example, and then each
Okay.
node, each process is kind of chunking up that particular section, reducing or finding something of that sort. This is pretty simple, right?
So
This is
okay,
not
so
giving us a
yeah, so
flavor
get
of. Hmm.
okay. So let's say in that case, let's say MPI gather. Now, if you're trying to gather data from first of all multiple processes, such as if you're trying to get some sensor data. You have multiple sensors, okay, and you have to make some decision based on different sensors, not just one, okay, and you uh, so in that case you gather data from all the sensors and then perform the operation, right? So
Yeah,
if
that's a
you
good
need
example.
to
Yes.
make any,
Hmm.
yeah, then if you want to let's say uh, okay, let's say if for reduce, if there is some kind of scientific simulation that you are trying to do, and you have to calculate the total energy that is received across multiple, you know, locations or processes. So the total energy will be an addition function of the
Hmm.
energy that is
Hmm.
utilized
Hmm.
in different scenarios. So that could be one example. And now, uh, you know, uh, in machine learning also, the MPI gather can be used to collect this different model parameters or gradients for multiple processes, whereas reduce can be used to aggregate these different parameters from different models, right?
Hmm. Yeah.
That
Yeah.
way,
Makes sense.
each
Makes
thread
sense.
is, yeah, yeah.
Right. And the example
So,
of
well, this
MPI,
broadcast,
ga
huh?
hmm, sorry, gather
Yes,
all and reduce all. What could be examples of these?
okay. So, uh, gather all will, so now, so there is, so there is no gather all, because gather all is basically gathering all the risks, right? That is only reduce all, I think.
I think I saw a variant for both of these two, gather all and reduce all, as in all the all the processes should get all the data, kind of a thing. That example was there. That's where the question.
Ah, okay, 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 okay. Yes, yes, yes. Yes, sorry. So, in case if let's say you have uh, so it would be okay, if you need some data from all the elements, all the sensors for calculating the total energy, as well as let's say the same data is used for calculating what is the average temperature, the different sensor data.
Hmm. That can
These
be done on
sensors,
single node. That can be done on single node, right? Why do we need to do it on all the processes that way? As in, why all processes should gather? Only one process can gather all the data and then find out an average and give it back, right? So,
what okay, what you have, if these processes are for, let's say, not just calculating total energy or this like
mhm,
1, 2, 3 cycle problems, but sim let's say if they want to do some kind of simulation or visualization using data from different sensors, those tasks are heavy, right? They need
mhm,
yeah, enough CPU cycles and computation. So for such tasks where there is a lot of heavy computation that needs to be done, and data should be collected from different centers sensors, and different simulations are done on each of the processors, that time you can use all reduce. So or even these climate modeling functions like finding average temperature, or even you know uh, it will like total precipitation and all those functions need a lot of data crunching. It is not just simple uh, addition subtraction, or uh, even all together we can we use it in image processing? Anyone can think of anything? Even in financial modeling there are like multiple different operations that are done, right? That is Same data can be used for, say, creating a portfolio value for a system, and also if you have some metrics to be calculated for risk exposure and all. So there also you can have multiple systems which will work on different, but the data remains the same.
Yeah. Okay.
Okay. So now why we need synchronization? We are doing so much communication. If we want things to happen without corrupting the data, ensuring the data is not tampered and it is in the state, we need synchronization. And one of the functions that you have in MPI is barriers, which ensure that all the processes which are there will reach the same point in the code before any of them can proceed. Function is MPI com word. We can actually try using this in the same function, because here also, as we can see, the broadcasting is happening later. So we can, what if we do not broadcast the value here? We first say you first complete the broadcast and then you do the other task. So I'm changing this, let this be local value. Okay, even now, sorry, even now even including the barrier, did I save? This should not be the case, right? Okay, so can anyone guess why barrier is not working here? We have separate example on barrier where the processes start, then they sleep for some time before the barrier, and then they can continue after crossing the barrier. We'll just try this out. Yeah, so MPI 0 starts, process 0 starts, then it reaches barrier, then 2 starts, 1 starts, 3 starts, and all of them reach barrier. Then once all of them reach barrier, the process 0 passes the barrier and starts working. That's some work, and then 1, 2, 3 starts.
Ma'am, can you once again explain the use case of this barrier?
Yeah, so so this MPI barrier is meant for, you know, all the processes. What happens is sometimes, since we start the processes at the same time, they start doing different tasks. And what if they do not, uh, if what if you want them to complete a particular task before they move to another task? So in that case, you can use a barrier which will like a physical barrier, which you can imagine when the threads are doing some task and they are moving forward, and then you put a barrier where all of them come and then they synchronize, they wait. So you do this particular task and barrier, reach that barrier, you cross that barrier only when all the processes have reached that barrier. So
Kind of a
uh,
checkpoint here.
yes, yes. So yeah, you can use this MPI barrier for debugging, you can use this for time management, time measurement. So before and after this barrier, you can and put timers. Obviously, synchronization is the important reason why barriers are introduced, but they can use for timing and debugging as well.
Okay. Okay.
So as I mentioned,
Ma'am,
you can create. Hmm,
sorry, can you go
yes,
down to the code screen? I would like to clarify my understanding as well. The code part of things.
yes.
Okay, can you scroll up where we have that sleep part? Okay, now assuming that we have, let's say, four processes, we have line number 16, which does a sleep. So numbers
Hmm,
allocated for each process would be 0, 1, 2, 3. So the
hmm,
sleep time for each process would differ, right? 0 into uh, rank
yeah.
is 0, so it is going to sleep for 0 seconds. Rank is 1, it is going to sleep for 1 second, 2 second, and 3 seconds. So basically what we are trying to simulate over here is there are four processes which are getting started with a different speed. We can resemble this to four people running a race kind of a
Hmm,
thing, right?
hmm, hmm,
So
hmm, hmm, hmm,
all of them will not run at the same speed. So there would be a slowness in a way. So
hmm,
that slowness is kind of mimicked with sleep. So each process sleeps for a longer period of time. Zero
hmm,
sleep
hmm,
for
hmm.
least, while three sleeps for the maximum amount of time. If we kind of
Yes.
reconcile this with the output, if you can run the output one more time.
Yeah.
Okay, so if we consider barrier now, if you can scroll up a bit
Hmm,
in the output window, if we scroll up for a bit. So assuming the slowness part, as in 0 is going to be the fastest, while 1, 2, 3 are going to be slower in that particular ratio. So if we consider the barrier part, 0 is going to reach the barrier first, then 1, then 2 and 3, which is being the output displayed over here. If you can scroll down a bit. So
hmm,
here
hmm,
we are forcing all the four processes to reach the barrier first before they can do
hmm, hmm.
anything after that. So until
Yes.
1, 2, 3 started, all of them reached barrier. Okay,
Hmm,
so
hmm.
zero has passed the barrier. Now, ma'am, this is
Yeah.
not clear now. So until 0, 1, 2, 3, all of them reach barrier. Zero should not be allowed to do additional work. Isn't that correct idea?
So, so all of them have reached the barrier, right?
No, if you see
Uh,
last but one line, three reach barrier. That would be
okay.
the
Three.
last
Hmm,
person
hmm, hmm.
reaching the barrier,
Yeah.
and until
Hmm.
they reach the barrier, zero, even zero shouldn't allow to be
Yeah,
kind
yeah,
of
yeah.
passed
Actually,
further, right?
all of them, all of barrier is meant for all the threads to reach and then communicate. Then only they can pass. They cannot pass like before the other. But
Correct,
yeah, because
correct. So
barrier
output.
concept is
Mhm.
common between different programming models, including CUDA. So where all the threads are expected to come complete a task and then reach the barrier and then only they can move forward. But yes, I can see the difference what you are saying in terms of
Mhm.
the way it is printing. So I will check why this is happening. Uh, if there is any reason why the IO communication, I'll have to check.
Okay,
But yes,
okay,
you
no
are right.
problem.
They all should.
Mhm.
They all should. reach one point at the same
Wait,
time. And then
right,
only
wait,
the next one should
right, right.
wait for everyone to come and then
Yeah,
move to next task. I agree. Yeah, I'll set
correct,
that up.
correct. Right, right. Assuming this situation to a situation wherein, let's say, there are four different people doing a task. Now, all of them will
Mhm.
require different amount of time to finish that task. And their
Yeah,
task result is something which needs to be consumed as part of subsequent process. So we will need to wait until all of them perform their individual task. So we force them
yes,
to wait until that barrier time, as in everybody completes in a way.
yes,
and
yes, yes.
and their
I,
individual output will be consumed by subsequent code portion and will do the computation based on the results
Well,
from all four of them.
and then what is the
yep.
difference between wait for all kind of thing and barrier?
No,
Are
wait is
they
for sending and receiving only.
okay? Okay.
Barrier you can put
Not for
anywhere in the code.
okay.
Mm. Wait and this because you in wait you provide the send function, na? Send, receive, buffers, those things. Wait is
Right.
meant for send and receive.
Ma'am, can this be even simpler example? As in, assume we teacher is teaching four students. She has written something
Mm-hmm.
on the board and she asked all four students to take it down. Every student will have
Mm-hmm.
different speed of writing. So until all four
Mm-hmm.
of them write completely writes it, she is not going to wipe the board.
Hold. Yeah, 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 yeah.
Can that be an example
And
for barrier?
that can be an example, or even let's say if you want to do there is a matrix and you want to do first do the addition and then maybe multiplication, and you've employed multiple threads. Okay, so they all have
Mhm.
to complete the addition of two matrices first before they start with let's say multiplication. If you do not wait, the data gets corrupted if all of them
Hmm.
have not complete.
Okay,
Like
as in we are making use of exact same matrix in order to get
do the
updated in a way.
yeah,
Hmm.
yeah, yeah, yeah.
Okay, yeah, thanks.
Okay, okay. Then. So we will learn about MPI in the next class because it's already time. So we'll start MPI and then we'll continue with distributed computing using MPI. Yes. Okay then. Yeah. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank
Thanks,
you.
Thank
ma'am.
you.
Ma'am, any idea by when the labs will be ready?
I have already sent a mail to yesterday to the team. I will
Mhm.
follow up.
Okay.
Okay.
Thank
Yeah. I just wanted to confirm whether you have access and I do not have. But so I'll follow
Okay.
up. Thank you.
Okay.
Correct, correct. That is
Thanks,
thank you,
ma'am.
important,
ma'am.
ma'am, because we will need to do hands-on now, right, in order to understand
Yes.
these
Yes.
things better. So,
Yes. Yes. You will need. Yes. And yeah.
yeah,
Thank you.
thank you. Bye.
Hello, ma'am.
Yeah.
Yeah, can you please share those code snippets with us so that it would be easy for us to go through them and also
Sure.
we
Sure.
can. Yeah,
I'll
Correct.
I'll create a folder and I'll upload them. Sure.
yeah.
Right,
Thank you
right.
so much.
Yeah, yeah, and even
So in the
the
Teams, it will be uploaded,
setup.
right?
Correct. Even
Teams
even the
file.
setup part, ma'am,
It's in.
as
Okay. Okay.
how
Okay.
to set
Sure.
things up. That is important.
Sure. Yeah. Okay.
Thank you.
Thank you.
Thank you.